So electrical circuits, there's actually only two types. One is alternating in terms of current flow, one is alternating, and one is direct current. The electrical supply to our homes and to just about every industry out there is alternating current. And that is typically represented graphically with a sine wave, like so. So whether it's current or voltage, you would have, I'm going to put down voltage, you would have a graph that looks like this, where this is the sine curve. And the reason it is the sine curve is because that is quite naturally the way power or current voltage is generated by a utility. And I want to go, I say quite naturally, I want to go over that in detail when we get into capacitors a little bit later on, and or maybe even inductors, and I'll show you how a typical generator works, and we'll go over some basics there. It's not going to be on the test. That's something that's going to be in Chapter 7, which we're going to skip. But just, so you know what's going on, I'll just explain it to you. And generators that utilities use to produce power quite naturally produce an output that's in the form of a sine wave. So that's how we represent it graphically. Now, in terms of the flow of current in a wire, the electrons would jump from atom to atom to atom, and that represents the flow of current. The electrons in the wire don't flow like that. They go back and forth, okay, in the wire. And the rate at which they go back and forth, though, is not linear. It's like this, right? So right in here, think of yourself on a roller coaster where the car is traveling very rapidly here. And so the electrons are going real fast, and then when they get to these sections, the speed slows up a little bit, okay? So think of it in that terms, but it's still back and forth, back and forth. So over time, the electrons don't go anywhere. If you could pick out an electron or a group of electrons in a particular point in the wire, over time they'd pretty much be at that same location. All right? But direct current, not so. So if you hook up a circuit to a battery where you would have electrons traveling in one direction only, that's called direct current. And for direct current, the electrons, again, if you could pick an electron or a group and follow it, those things would travel along that wire over time. In a loop, they would go back to the starting point. So I had years ago, when you take physics, there is this electrical circuits, electromagnetic field theory, that's all covered in physics as well as electrical engineering. The approach that they use is a little bit different than in engineering. But I had a problem one time in a physics class that if you had a circuit 12 inches on a side, a battery, wire, square circuit, 12 inches on the side, and you flip the switch and it was direct current, how long would it take for one electron to make it from the battery terminal all the way around that circuit? You're talking 48 inches. All right? So, and I think, the current was like 5 amps, something like that. So what do you think was the order of magnitude of the answer? Was it an hour, a couple minutes, an hour, a day, a week? How long do you think it would be? Take a guess. 2 seconds? Okay. What do you think? About a month. Okay? Takes about a month. When you go through all the calculations So we're talking about little tiny things here. These electrons, they're very small, and so when you factor in the cross-sectional area of the wire, and I think they used number 12, you know, house wire, and they had like 5 amps, and those were the basic parameters. I actually still have the problem. I kept that's one of the few books I kept in college, but I actually still have the problem at home. But it takes about a month for 48 inches, so it takes a while. Now let me show you something. Let's just say we had alternating current, but I got rid of the negative portions. And my waveform looked like that. Would it still be alternating? It's not alternating anymore, okay? It doesn't look like it, but by definition, that current, it flows this direction here, and then it stops. And then you have that gap, flows this direction and stops, okay? So don't be deceived by the shape of the waveform. If there's no negative part, then it's direct current. Same way with any other waveform. So this would be, by the way, that would be the waveform that you'd get out of what is known as a half-wave rectifier, where you're trying to convert alternating current to direct current. That would be the starting point for a half-wave rectifier. So let's just say you had this. Alternating or direct?
That's still direct, right?
Still direct,
Because
it's not below the negative, not below the 0 axis, okay? All right. The other thing that we did not cover with regard to circuits is that there are two basic philosophies in circuit design, and one is analog, one is digital. So in analog circuits, the current and voltage could assume any value, almost any value. You have continuity there in an analog circuit. Whereas in a digital circuit, the voltage and current can only assume certain discrete values. So just about everything today has gone digital. Certainly the equipment that you have in front of you is digital. But analog devices are still being produced. I have an ammeter. It doesn't look like an ammeter, a conventional ammeter, but I can measure the current flowing in a wire without connecting anything to it with this little guy. And what I do is, if this were a long wire, I would just clamp onto that like that. Current flowing through a wire produces a magnetic field, and when I clamp onto that wire, there's an iron core in here that intercepts the magnetic field, converts it to a current or a voltage reading, and this happens to be an analog meter because it's got a needle there. So you can see if I'm measuring current, it could be anything, any number whatsoever. And then I have the same kind of deal here. This is a digital clamp-on. Same meter, looks the same, but the readout here is very discrete values. Now I actually won this as a door prize, 20-some years ago, and I actually love that little meter. The reason I like this is because if I'm measuring the current in a motor, for example, the motor's not running, and somebody flips the switch and starts that motor, the instant, just for a second, the instant that motor starts, you'll get an inrush of current that's maybe 6 or 7 times the current that you'd see when that motor is up and running. They call that full load current. And the inrush is caused by the fact that the magnetic fields in that motor are just expanding very rapidly. The motor won't turn unless those fields are present, and that inrush that buildup of the magnetic field causes an inrush, And I can see that here with that needle. It'll jump and then come back down to whatever value it settles in at. I can't see anything on this. It's too quick. This meter's not fast enough to record that jump. It's only a fraction of a second. So even, this has a max-min feature, even then it doesn't catch it. So I actually like this one better, although today if you get a meter like this, or here I have my Fluke meter, which is a conventional digital meter. Very few people get analog versions of these. It's all digital, okay? So I love that thing. It has all kinds of features on it. Here's the analog equivalent of this meter. I wish I could use that. One of the fuses is blown on that, but you can see the needle, and I can read almost any value with that. Kind of an old guy there. So analog versus digital. And then we have, the other thing is linear versus nonlinear circuits. A lot of the stuff we're going to be talking about, up until we talk about capacitors, is going to be linear. So that's a linear circuit is where the relationship between the variables is a straight line, something like that. So you might have voltage here, current here, and the relationship, or it's just capital I. The relationship is something like that, okay? Straight line. If I had a device that was nonlinear, the relationship would perhaps be something like this, or something like this, where you really couldn't, you don't have that straight line. So this is linear. And this is nonlinear. We're going to be dealing strictly with linear till we get to capacitors and inductors, and then all of a sudden, whammo, it's going to go to nonlinear. Okay, makes sense? Any questions? Okay, one of the things that we were talking about last week about resistance, and we were looking up the values of resistors based on the color of the bands and all that good stuff. But the one thing that I didn't get to is a parameter called resistivity. So resistance is an extrinsic property, resistivity is intrinsic. And by that I mean it is only dependent on the material itself. So if you're looking at the resistivity of copper, and you want to calculate the resistivity, if you had a conductor that looked like that, or a conductor that looked like that, a little bit smaller. I think this is a size 2/0, I believe, a little bit bigger than this. This is number 6 wire. I probably should go over that, which I'll do. These would have different resistances, but the same resistivity. So resistivity is similar to, let's say, the density of a material or the hardness. Let's just look at density. Density would be the mass divided by the volume. So the mass is a function of literally how many atoms there are in a particular volume of material. Mass divided by volume gives you density. And if I were dealing with a piece of wood, let's say pine, Yeah, you know, it doesn't matter whether I have a board that's 20 feet long or 10 inches long. If it's the same type of wood and everything else is equal, I'm going to have the same density. And so, in a similar way, it doesn't matter. Resistivity does not have anything to do with anything but the type of material it is, okay? And here's the relationship between resistance and resistivity. This is for a cylindrical cross-section. Resistance is equal to resistivity times the length divided by the area. So the resistance is in ohms. The length, let's just say metric, the length is in meters. The area is in meters squared. Cancels that, and this guy here, resistivity is in ohm meters. That's the dimension, and the symbol that I wrote is the Greek letter rho. Okay? So resistivity, the dimension is ohm meters, it's the Greek letter rho. Let's go over wire sizes. I kind of skipped through that real quick. So on page, I think it's 63 in the book. Yeah, page 63. I probably won't have any test questions on this, but of course this is not your like house wire. House wire is much, even for this, it's much smaller. But when you get into commercial and industrial work, you're going to end up with conductors that are all over the place. Sometimes they're the size, they have the cross-sectional area of a $50, and sometimes you use number 12, but the number of a wire is in terms of it's called its American wire gauge, AWG, and the higher the number, it's kind of a reverse relationship. The higher the number, the smaller the wire. So telephone wire is like 24 AWG. House wire is 12, so it's a little bit bigger. This is number 6 wire, so this is good for like 50 amps. That's number 6. Here you have, let me see what this is. This guy's number 2, all right? So it's a smaller number, 6, 2. What happens when you get to 0? Well, then it gets crazy. This is number 3/0. So when you get, so wire sizes go number 2, number 1, then it goes, nobody ever says, it actually, the wire size goes to 1/0, number 0, but nobody ever says that. They say 1/0, all right? Then 2/0, then 3/0. This is like 200 amps. It's good for 200 amps. When I say 200 amps, that is like the maximum safe current you want to run through that cable without causing a fire. It doesn't mean that it won't take 300 amps. It probably would take maybe 220, 230, but at some point the insulation is going to melt. Okay, so 3/0 is good for 200 amps. Then it goes, the next size up is 4/0, and then you have 250 MCM. Is somebody looking at the chart? Or doesn't? Oh, the chart doesn't go that high. Okay, this chart stops at 4/0. So after that, you have 250 what they call MCM. In the old days, it used to be MCM, which is million circular mils. Today, it would be 250 KC mils, which is 1,100 mils. I don't know why they changed it. But they did, the code folks. So these just refer to the diameter of the wire in circular mils, which is 1/1000th of an inch. That's all it is. Unless you're in the business, in the industrial business or commercial business, you'll never see a wire like that, you know. And the sizes go up to ungodly numbers, especially in aluminum. 2,000 KC mils. I mean, they're huge. But you just don't see that in everyday use. Okay? So I'll just pass those around so you can check those out. So that's that. So I just wanted to give you a flavor for if you ever see those markings, even guys who are taking mechanical, maybe you have to work on a piece of HVAC equipment or a piece of rooftop equipment, and your boss says, "Hey, go up there and check out the motor or the fan or whatever." And if you get a chance, open up the cabinet and tell me what the wire size is. You know, sometimes you have to do stuff like that, and you should know that by law, believe it or not, there is a law that says all wires have to be labeled every 2 feet somewhere. Usually when you want to look at a wire, the labeling is on the back side and you can't see it with unless you have a mirror. But by law, that's the situation. Everything about that wire has to be repeated every 2 feet along its length. The type of insulation, the specifications, the wire size, all that good stuff. Okay? Okay. Who has questions? Any questions? Make sure you write that down on your file cards, by the way. Oh, Russell, one thing I didn't say. You weren't here last week. When I give a test in this class, it's not open book, but you can write stuff down on a file card. So whatever, front and back, whatever you write down is fine, okay? Does anybody else need a file card? Okay. Well, one thing, there's another thing that I'd like to go over that is actually not in the book. And I'm thinking that some of you have already had this. For the last semester, most of the students did, but there's some who didn't, and it's called dimensional analysis. And the reason I want to go over this, thanks Jared, is because a lot of times when you're working on a project, you'll be going through data sheets on equipment or trying to do some work, and you'll see that Some manufacturers will specify a parameter different from other manufacturers. And I'm going to use just distance as an example. If you're looking for let's say the resistance of a wire, if you are in the utility business, resistances of wires are ohms per mile, because I mean transmission lines are quite lengthy, so they don't bother giving you the resistance of a aluminum wire or whatever in terms of feet. It's always per mile. And in other situations, you might get the resistance of a particular wire per inch. So you have to be able to start out with the manufacturer's data and convert it to dimensions that you're looking to work with. Sometimes you have the same parameter over here in one set of units, and sometimes you have the same parameter over here from another manufacturer, same parameter but different units, and you have to be able to convert those to one common set of units so that you can do your calculations. And so the way you do that is dimensional analysis. Now, the whole concept of dimensional analysis is based on the notion that if I multiply a number by the quantity 1, I'm not going to change the value of that number. All right? So that's the basis. If I multiply 5 times 1, I'm going to get 5. I haven't changed anything. All right? No, I haven't put any units up there yet. Well, I can represent the number 1 very creatively. I could say 5 times 12 over 12. 12 over 12 is a 1, isn't it? So that's still 1. And if I multiply 5 times 12 over 12, I still get 5. Well, what I'm going to do is just I'm going to extrapolate this concept, but I'm going to add units. For example, if I have 5 feet and I want to convert that to inches, I know that 1 foot is equal to 12 inches. So if I create a fraction like this, in effect, that's the same as multiplying by 1, because 1 foot equals 12 inches. Okay? You with me so far? By the same token, 12 inches, I can write it this way. It's equal to 1 foot. So I can flip those fractions one way or the other, and I haven't changed anything. Now, if I want to take 5 feet and convert it to inches, then what I want to do is use this fraction here. I want to multiply that times 1. And I'm going to do it this way because my feet will cancel. I have a foot in the denominator, but here I have a foot in the numerator. All right? So I'm going to multiply this times 12 inches over 1 foot. And I'm going to cancel the dimensions just as I would a number. In this case, my feet cancel. The only thing left is inches. And I multiply 5 times 12, and I get 60 inches. All right? So let's just say I have 10 miles. And I want to convert that to inches. It's going to be a little bit more involved. So I've got, let me just think here, 1 mile is 5,280 feet. That's one of my relationships. So I'm going to just write 1 mile, convert that to a fraction. and keep that right there. And what did I say, inches? Is that what I'm going? Okay, so I have that one here, I've converted miles to feet, and I've converted feet to inches over here or over here. I don't know how this is gonna work out. So what I wanna do is get feet up on the top here. So let me just reverse this. So if I do that now, I'm gonna put 5,280 feet is equal to 1 mile. I'm still not there, I gotta get to inches. And now I'm gonna put 12 inches is equal to 1 foot. And I'm now gonna cancel my dimensions. So I have miles that cancel there, feet that cancel there. So 10 miles times 5280, Jack, I forgot my calculator. Can somebody multiply that?
2,800.
What'd you get?
Isn't it 52,800?
52,800 times 12.
63,36.
Wow. Okay, so 10 miles is equal to 63,360 inches. And that may seem like a somewhat trivial example, it's only distance. But when we get into ohms and volts and farads and all that good stuff, and that is a very useful tool. Okay, you get into manufacturer's data books and you start converting units, and you can really get yourself messed up in a hurry. So just remember that all you're doing is multiplying by 1, and flip your fractions so that the dimensions cancel. Once you can cancel the dimensions, be mindful of the numbers. You still have a 10 there that has to be multiplied by 5280, and that has to be multiplied by 10. And the only dimension left then is inches. Okay, so that's the basic, you'll get it. If you've never done this, you'll get it. That's the basics of dimensional analysis. So that's not in the book, but it's important. Royce and Alex, do you have any questions on the homework? Is there anything? No questions? Okay. Can you, before the end of the class, can you hand that in then? Okay, let's reinforce what we've learned. I have a lab here on calculating resistivity. So let's do some calculations just to make sure that thought is reinforced. So I mean, this is going to be graded, but don't think you can't look at your book or ask me questions. I just want to make sure you understand the principles. Or you can talk to one another, excuse me, you can talk to one another, that's okay too.
This is what I didn't do last week. I didn't get to it. What? Resistivity? Yeah, resistivity. No. Who is he?
One of the advisors. He also lives with the veterans. I gave him a call last week, trying to get in touch with him.
That was your role.
I was running.
So resistivity is rho, is resistance equals rho L over A. It is right here. Resistivity is a intrinsic property. No. So that's resistance in ohms, the length in meters, the area in square meters. Okay?
Okay.
All right? And this is the resistivity of whatever is over the copper, which is an intrinsic property of density.
Okay,
So resistivity, so you're given, and that's in ohm meters. So what rho is ohm meters. Ohm is 1,000 meters, and the cross-sectional area is this. You just plug it in and you get the resistance of that particular one. That's rho. Divide that by 1,000, which is ohm. And divide by here, which is
the one is $5. It's left, if I didn't know what to know.
And I forgot all things I forgot my calculator. Not regarding it. If you are, you do batteries.
There was one, my wife's one there, TI-89.
The TI-89 calculator? Yeah, it's not bad. Yeah. I'll have to use my phone.
Correct, for resistance, yeah, for resistance, yeah. That's the one. That's this. Okay. So these two are multiplied together in terms of dimensions. That cancels the meter squared down here. The only thing equals was to multiply that times that divided by that. Did you get it?
No, I don't mind your first one. I multiply that. What is that?
This, no, this is scientific notation. So that's all one number. I'm not sure it's true. Exactly. Oh, here. So this number, see this? That's equal to 1.7. See that? 1.7 minus 8. that's EDX. Yeah, that would be it. Yeah. Okay, times divided by 0.00012. No, minus 8. That's minus 8. Times 1,000. We probably don't have extra ones. Do you have any other applications on there? Well, I think you can use that one. There's the extra. Just use that one. So it's 1.7 exponent minus 8. Okay. Times 1,000. Yeah.
Yeah, I want to go over these. Okay. Yeah, just keep that, I want to go over these. Yeah, really.
You said we'll go over them?
Yeah, I want to go over them.
Okay.
Just make sure that we're on the same page here. you done? Okay. Oh, if you need this, you can let me know. All right, let's go over these. So the first one, did I get those right? 1.7 times 10 to the minus 8, is that what I have? I don't have a paper. So we're just going to cancel our dimensions. We have meters times meters, and that cancels the meters times meters down here, meter squared. And so the only thing left in terms of dimensions is ohms, and that's what it should be. So that's a good way to check that you've got your equation correct. So what do you get? Scientific notation, what do you get with this? What's 1.7 times 10 to the minus 8 is divided by 0.00012, what is it? I don't have a calculator. 0.14 something?
0.141.
0.141?
6.7.
Is that what everybody got? Anybody get anything different? Okay, all right, so that's the first one. Does everybody understand that? That's more important, I guess. Everybody understand it? All right. Number 2. I don't have my sheet here. Resistivity of aluminum, 2.8 times 10 to the minus 8, got the transmission on 30 kilometers. Okay. So we have 2.8 times 10 to the minus 8 ohm meters for resistivity of aluminum. We have a transmission line that's 30 kilometers. Remember in chapter 1, kilometers is 10 to the cubed meters, okay? I'm going to write that. What was the cross-sectional area? 0.0003
Yeah.
meters? Meters squared?
No, that's it, just meters. Meters in diameter.
Should be meters squared. Oh, that's the diameter. Whoa, okay, getting fancy. So I gave you 0.0003 meters as the diameter. Well, in order to get the area of a circle, so that would be pi times 0.0003 is the diameter divided by 2. That gives us the radius. Now we have to square that. What was the, did anybody do that calculation? Area, okay, 3.14. Times Is that what you got? 7.065 times 10 to the minus 8? Wow, okay. So we have a little bit of a side calculation going on. And this diameter equals this area, which now we can put in. Okay. So meters times meters equals meters squared. We have ohms remaining, and that gives us what?